plasticity. But that's the first thing we're going to do, is establish a little bit the difference between them. I think I still get them confused every once in a while, because they're both important. We deal with them all the time, but they are fundamentally very different, and hopefully you'll get that out of today's class. We're going to talk about stress states. The simplest stress state is a uniaxial tension that we talked about a little bit in the previous class, but you can also pull on a piece of metal in two directions. We do that for forming fuselage components on aircrafts. We want to get a complex shape, so you really stretch form the sheet of aluminum to get its nice curvature in on the two axes. We're going to talk after that most specifically about plasticity and what triggers the beginning of plasticity and how it evolves after that, and that's called strain hardening. And we'll talk a bit about the implications for the rest of the class of those concepts. So as we go through it, any question you have, we have a very diverse background, so some of you may know more than what I'm presenting. Some of you may struggle a little bit with some of those concepts. So I'm trying to make it so everybody can follow at least a good amount. When we're talking about elasticity, hopefully everybody has in mind that you have this, and we're talking mostly about crystals today. So things that have to do with thermoplastics, for example, that are amorphous, like polycarbonate, is slightly different. I'm happy to talk to you about it, but it'll be too much today when we're trying to just separate apples from oranges to get into those types of structures. So we're talking about something that's organized. So I'm going to put the atoms here, and the distance between them, probably seen in one of your physics class, is essentially the minimum energy. The distance between this atom and this atom is a good compromise between what attracts them together and what brings them apart. And we can see that on an energy curve that you may or may not have seen. So I'm putting here the energy on the vertical axis, and I'm going to put the radial distance between two atoms that are next to each other. And what happened, the reason we have crystals is that energy goes down to a certain value and then goes back up. Eventually, when you go to a large distance between two atoms, they don't interact with each other, so there's no interaction energy anymore. If you try to bring them too close, you have a strong repulsion from the nucleus. So that's the idea here that we're working out of, that there's an equilibrium distance between the atoms, and what we do in elasticity is we just change that distance by a little amount. And by a little amount, I'm putting on the slide here less than 1%. A lot of times it could be even 0.1% for metals. So when you think of it, it's not a big change. It used to look like this, and it will look like this after you pull on it. But it does give you a resistance, because you're going to go from here and start increasing your energy here for the bonds. And that's really why we have Young's modulus. Any question for elasticity? All right. So we're moving on to plasticity. Plasticity now means we're going to change the shape. So if we have this cube here, make it a little bigger. I want to transform it. I want to say, take these, the bottom, and move them this way, as opposed to those on top that would stay at the same place. That would be a perfect shear, right? So it'll do just like this. Now, we'll not be doing it as a one-shot operation, because what it would mean if we try to do it all at once, at some point, this atom is going to be right next between two atoms now. So there's going to be a whole lot more energy associated with that state. And it'll be the same for the other one and the other one. So all together, the atoms will have to move from their equilibrium position. So what happens in reality is we have defects in the crystals that allow for just one step at the time to take place. And that requires less energy. We call those dislocations. We have it here on the schematic where at the beginning we start with a square, and then we start moving a little bit. These four atoms, we push them to the left and start changing some of the bonds. But when we do that change, as you can see on the other side, far away, there's no effect at all. Over here, it's still the equilibrium elastic distance. So doing it one step at a time is a great opportunity to allow for what we're trying to achieve as change in shape by shear, but by little steps. And just make sure everybody remembers it. We'll go to a very practical example. We have a rubber mat on a floor. Make it 10 feet long. That's the entrance to the infinite corridor. I want to put on it 1 foot. And I said it's rubber, so I got a friction coefficient. I'm going to say 0.7 with the floor. And it's a very heavy one, so 100 pounds. So if I decide to pull on it, the force that's going to take is approximately 70 pounds. For 1 foot at 70 pounds. It's doable. I mean, I can do it, but I have to continuously pull on it. If I decide to stop, go the other way, I'm not going to reach my objective. The difference, if I start making a little roll on the carpet at the beginning to reduce the length by a foot here. I'm sorry. So let's say I made this about 1 foot high. I can think about the proportion. Maybe I have to lift 10 pounds to do that, to create it. And then after that, I can literally just push on it a little bit and get to the other side. And I'll reach the 1 foot offset without never having to apply more than 10 pounds. And I only need to apply that 10 pounds. We'll put 10, 15 because with the ratio I have. I only need to do it once at the beginning. And after that, if I decide to take a break, move back a little bit, go again, it can take a long time, but it's not going to require me a whole lot of energy. There'll be some friction, but nothing like pulling it like we talked about on top. So for plasticity, that's what you have to always remember, that it goes towards an easy path. But by doing that, what it means is now it takes me time. I have to make that fold on the carpet. It doesn't happen right away. If I decide to put a 70-pound, I just put it like we do in elasticity. We can play the guitar, we can do all sorts of things with elasticity that we cannot do with plasticity, because now there's a time and effort in creating this fold. So keep it in mind, because it's not a class we can spend, in crystallography. I'd love to talk to you about all these types of dislocations, but all of this is related to dislocations, and it makes the big difference between trying to do it all at once and using the randomness, because what happens is under load, these dislocations, those defects in the crystals, they'll move. So eventually the fold's going to get on the right spot, and you're ready to go if you're willing to wait. And that's why it's time dependent in plasticity. It always comes down to how long are you going to wait before it deforms. And it also explains why steel at low temperature becomes brittle for impact loading. So if I really try to use a structural steel in Antarctica, I have to be very careful about what I'm doing, because some of these steel won't be able to make that fold at low temperature, and therefore they'll be brittle. They won't be able to deform plastically and accommodate to changes in the structure. So that's really what, by crystal plasticity, that it's very different, right? I mean, if we look at the schematic, at the end, some of these atoms move by 1 atomic distance as opposed to where they were at the beginning. So that's 100% as opposed to the 1% we had for elasticity. And there are very complex ways by which they do that. And that's why we can't think of them as just being, oh, it's deformation. So one is very small strain value. It happens all the time in any application. The plasticity sometimes is permitted for part in service, but a great majority of the use is for forming. And that's what we'll talk about the next few classes. Yeah, we've really covered that, except maybe the reversible aspect. The reason why plasticity is not reversible is when I go and create that fold and propagate it in those crystals, I have to go through a lot of obstacles, and I'm going to create more obstacles. It's a war field. And after the war is over, you'll have to clean up if you want to come back the same way. Okay, so and I really mean it. I think it's a good way to think of it. I deformed the metal one way, I can't bring it back. You guys try that? You bend a piece of metal, try to bring it back perfect straight. It's just going to go deformed on one side, go deformed the other side, do all sorts of things. So the best way, if you really want to bring it back, is you heat it up. Clean up the battlefield, and then do it. That will work. So you create that history, you create those permanent changes. Well, they're not that permanent again, because you can have an annealing, which is heat treatment at high temperature, that would really remove a lot of the interactions you created, the little knots here and there. It's essentially, the key word would be dislocation multiplication. It happens a lot. And really the way to get them out is to heat up the material. Now, I mentioned that plasticity is used in forming. Now, elasticity, we all know, is used for a large number of applications. A lot of times when we talk about springs here, springs are essentially most often pieces of steel that we will deform and deform and deform, multiply the dislocation, make a lot of fold into them. So now when we put them in your car, they're very stiff. They don't deform anymore. They have so many obstacles built in that it'd be really hard to create a permanent deformation in them. So that's how we raise the yield strength of a lot of metals. Yeah, let's circulate these around. These are samples that really relates to the heating we talked about. It's the same alloy, it's copper. There's one that was at 700 was the heating temperature. We have 600 and we have 450. And one thing you'll see is they don't have the same length. Also look in the center, some of them, especially the 600, really has an orange peel type of effect on the surface. That has to do with the grains, and we'll talk about that. But just take the time it takes to circulate them, so when we're at that point, everybody already had a chance to see what the samples look like. The one that stretched the most is the one that was heated to the highest temperature. Okay. Stresses. The reason we make this a topic of the class here is your stress state is always going to dictate the plasticity you'll have. So if you're going through a rolling operation or any forming operation, there'll be some restraints on the material you're working with, and that stress state will determine whether you'll be able to make it to shape all at once, whether you have to do it in multiple steps. If you manage to minimize the tension when you're forming any material, you increase your likelihood of success. And that's why in forging, for example, they're very careful. If we make the head of a screw, we have to be very careful, because now we're going from a flat rod and we want to put an end on it. Well, means I have to expand the metal, and in expanding it, there'll have to be some tension somewhere. So we have to control it so it doesn't reach a critical value and we don't form defects in the material. And that's for those reasons we need to know our stress state at all time, and it will vary a lot of times. But on a simple case, we will say that if I draw a box like we did at the beginning, I can always find my stress state. If I take a piece of a component or something I'm forming right now, and I take out a box, that's the free body diagram now. So I can put forces on a free body diagram so it stays in place. And the state, the condition of the stress shouldn't depend on how I draw the box. So that's just my way of looking at it. It's the same way if you do a free body diagram in a static problem. It doesn't matter if you cut the problem in three and bring it back together. if you have enough pins that your system only has one solution, you can do it the way you want. And it's the same thing here with that cube. I can draw it this way. I can decide, oh, no, I want to do my cube like this at the same location for a different reason. And it will be the same solution. It would be the same state of stress. And that's the concept behind those principal stresses. At least that's the way to remember them. That I can make any box I want, and from there calculate the principal stresses. So the principal stresses are those where there's no shear. I'm always going to be able to make a box somewhere in the material in an orientation where it's all in all three directions. It's tension or compression. No shear. And the reason to do that is just to simplify the analysis. It doesn't matter which way I draw it with respect to the material fracturing or the material hardening and all those phenomena, but for treatment, instead of having 9 components of stress, I only have 3. So it really simplifies the analysis, and that's the main reason we keep referring to principal stresses. In forming operation, a lot of times we know them by the geometry of our load applied. So it's actually simpler than what it looks like here. Here we have formulas where you have the XX and YY and all these stress components. Is you take them from here, you take them from this orientation. At the end of the day, they'll give you the same value of I1, I2, and I3. And therefore, the same values for the principal stresses. So the principal stresses, the equations are at the bottom, because you have 3 I values that you determined from any of those boxes. Pick any of them. And that's, so you use equation 1.11 with any stress coordinate system. It gives you I1, I2, I3, and then you use the 3 other equation 1.12 to determine the principal stresses, so sigma 1, sigma 2, and sigma 3. And it works. But we're going to talk a little bit about how we decompose it. And the reason we decompose it, because I can put as much pressure on a crystal and it's not going to change its shape. I don't know how soft we can take something, but if you drop even a sponge, I think, in the ocean very deep, it's still going to look like a sponge. It's going to be smaller, but it's not going to become a rope. It's going to elongate, especially in one direction, or change its shape. So with the idea that when we have those principal stresses, if we take out the pressure, so the value of those forces here, normal forces, that are the same, what we're really left with now is what is changing the shape. And that's what we call the deviatoric, and that's on the right-hand side here. Now we still have some shear values here, but if we're working in the principal axis, they are 0. So we only have 3 components, and it's those 3 components that are going to change the shape when we deform. So the reason for presenting this concept is to make a big distinction, make it clear to you guys that pressure alone will not deform plastically any metal or plastic. It's the difference in loads from this direction to this direction to this direction that will create the deviation, the change in shape. And von Mises has been one of the first ones to recognize that. And as you can see on top here, that's what he's put up as the key equation. He says if I have enough difference between the square of my differences here between the top face, the side face, the front face, I'm going to have yielding. I'll reach the yield point on the curve in 3 dimensions. So this is all very general 3D dimension. And I pulled a little schematic for you in the middle of the page where if you are inside that cylinder, the cylinder has an axis that's right in the middle between sigma 1, sigma 2, and sigma 3. If you're in there, you can put as much stress as you want. You can compress this, or you can put tension on it. It will not yield. But with the differences, there's only so far you can go when you start having a difference between this one, and then you'll start yielding. So it's really a principle to keep in mind that it's a comparison of the tension in a different direction that gives you this permanent deformation that allows for shear. Because at the end of the day, and we looked at that crystal, what happens in the material is shear. So it makes sense that if you pull by a different amount in one direction than the other, you're creating conditions for shear in the material now, as opposed to just trying to expand it as a pressure or compress it. That was probably the most theoretical aspect that we're going to cover today. Now we're really going to try to capture off of it for a very specific application. So a 2D representation here means we're taking one of those components, sigma 2, and we say it's 0. So now we're working in a plane, and our cylinder has become this yield shape, the yield locus. And if we apply a tension, if we go back to uniaxial tension from a tensile test, we'll be right here, and we'll still start yielding at Y, the yield stress. But we can see now the effect of applying a different type of loading. So if instead, and I'll reuse this, instead of applying a tension only, so we have tension. And if I go and apply a compression of the same amount in the other direction, we're going down on that curve where one of the stress component is equal to the other. So we're down here, it's pure shear. So it will take less force, less stress if I add a compression in the second direction to create yielding. And that also relates to what we talked about, where at the end of the day, we do want shear in the material for yielding. But the whole von Mises criteria and calculation approach just allows you in 3 dimensions to figure those out, to figure out how much shear you have as opposed to hydrostatic pressure, and am I in a yield condition or not. So that's what I'm hoping you come out of this class with, that we use it when we don't know exactly the equivalent effect. I mean, we know for a tensile test, yeah, you pull and you have a deformation, and that's how we arrive to these engineering properties. But what if I have tension on both sides. Well, tension on both sides on this schematic brings us here. So we're able to take more stress in two directions before yielding than we are able to take in just one direction. And that all comes back to that difference of principal stresses equation, the equation we just talked about here, the top equation. Because we're reducing the difference. So now we can apply more stress before it yields. Okay, so we use von Mises to know when it will start yielding. After you start yielding, I talked about all sorts of things that happen for hardening in the material, and we'll need another framework for taking care of that. The von Mises equation, the way it starts, doesn't tell you. It only has one material constant, which is C1 on this page. So C1 will change depending on how you treat the material because of hardening. It takes the material as isotropic, which means if I run the tensile test in the horizontal direction here or in the vertical direction, I get the same stress-strain curve. And that's generally not the case. So there are limitations there. And then I say it's only for very ductile materials because the criteria allows you to put as much hydrostatic tension in 3 dimensions that you want on the material, but in reality, eventually, it will break, it will create voids, microvoids, and eventually fracture. It's just not something that the equation includes, but we take it into account separate. All right, now strain hardening. And you've seen those samples. Those samples were able to stretch about 30–40% before breaking. If you didn't have hardening, it will not deform this much. If you had, say, no hardening, and I take a straight piece, and then I have a little deformation, see here, in shear. So I'm reducing just a little bit the thickness here. The deformation is going to continue there as opposed to going to other location and making shear at different location. And some metals, mostly amorphous metal or bulk metallic glass, will have this type of behavior where it doesn't spread much over the distance, and therefore you don't get elongation before you break them. So it's really the strain hardening that allows to say, okay, yeah, I took some strain here, I changed shape, now I have even a little notch effect on the surface, but no, it's your turn to deform because now I'm stronger. That's what strain hardening really is. And when you look at it from stress-strain curve, when you average out all the deformation that's happening in the sample, we have this key equation of the stress. Typically is a power law. So there's a constant that's defined from the initial yielding, and then you have an exponent to the strain. So this is your plastic strain value. As you increase the plastic strain, your stress going to go up based on a certain hardening coefficient. So it's exponential. So the value of that n typically be between 0.1 and I'll say 0.3. You could have higher, but a lot of times it's in that range. And that's what is shown here for an example of aluminum where we're plotting it on a logarithmic scale which makes it easier to find that exponent. If I go and just do the log here of the stress, this is a constant, so it's not going to change. So I'm going to have the log of the strain. So this value here is the slope. And that's really what this schematic is showing you, that they went on and looked at the slope to know how much hardening the aluminum has. Now we'll go back now to what it means. The hardening allows for strain redistribution, which is good. It means that you can rely on the material becoming stronger locally, so the strain goes in different direction and you change the shape, and when you bend the bar, a lot of times it'll have a nice curvature as opposed to having a kink in it, a solid bar. Now it takes more force in forming, and that's definitely something Professor Eager is going to talk about, where in forming sometimes you want to do it hot, because when you're in hot condition, I talked about those battlefields that creates when you deform, so you can get rid of them as you go, so you don't have as much hardening. You recover from the dislocation multiplication as you go. We can make a big advantage of work hardening in products. Copper pipes, for example, tend to be very soft unless you cold draw them before you in the final step of making the tubing, and that's how we can put more pressure in them, or they don't sag. There's a great variety. Most fasteners, you want them small so you can penetrate metal or wood, and you don't want them to be too ductile so they don't break when you put them in. So they'll be cold work a lot of times. Springs, a lot, I don't know if it's half, but there's a great variety of products that we use that have taken advantage of work hardening. Okay, we talked about the stress strain curve, and I told you, think about the fact the material keeps becoming stronger. All right, and this gives you a formula here on how to go from what we call an engineering stress strain curve to the real true stress, true strain curve. And the reason why there's a difference between them is the way we plot normally the curve in the laboratory is based on the initial area of the sample. We measure the width, the thickness, we get A, and we keep that. But in reality, that A changes. So I'm just going to elaborate more on that here. We're going to start over. We're going to elaborate on what does the peak of the stress strain curve really means. And the stress strain curve essentially talks about the load. That's what it says. And the load is the stress times the area. Everybody? Now, at the peak load, we know that there's no variation in load anymore. We just reach a plateau. So we have dP is 0, but it's also here the variation in stress times the area, and the other way is true as well. So we have sigma dA. That's the condition at the peak of the stress strain curve, so it's the point B right here. if I organize this, I essentially get the d sigma over sigma is minus dA over A. All right. We have to work with the dA here, so we'll do that just now. The volume is another thing that is not varying. So that's A times L. It's not varying. So it's equal to 0 here. And it's L dA plus ADL. So if I organize this one, I have minus dA over A is dL over L. Anybody knows what dL over L is? Great. So, we essentially, why did I have the differential? I lost the differential here. It doesn't go to 0. That's the point, because so you have sigma here, and you can actually reuse this equation with those variables to find that the value at B here of the true strain is your strain hardening exponent n. And that should make you think that it really doesn't relate to fracture. I mean, does it? If the peak of the stress strain curve is the strain hardening exponent value in terms of strain, it's really a property related to work hardening of my sample as opposed to being related to a fracture resistance. Now, this is where we can't do a whole lot, by hand calculation at this point. The concept I want to introduce is that von Mises cylinder we talked about. It essentially grows when you deform, and you can determine the new shape based on the concept of normality. It's explained a little bit in the text, and what it means, for example, for a uniaxial strain is that not only you get a strain in one direction, but you also get strain in other directions. So you have a shrinkage in a corresponding direction, and that's given to you here in this schematic. So the yield surface will grow perpendicular to itself locally. But that's if I'm in uniaxial tension. So I'm starting over here. I can grow the ellipse this way. It may grow the ellipse the other way as well, but not necessarily in the exact same proportion. And that's where the whole von Mises concept falls apart a little bit. So to wrap up that part on deformation, one thing I hope you realize is if we deform, we don't lose atoms and we don't create them. So our volume stays the same. And a lot of times if we were to quiz you, that's something we will quiz you on, because it helps you add an equation. We've done it right here. It helps you add an equation to determine the solution. So the metal and most plastic will not change significantly of volume when you change them shape. Solids, obviously. We talked about rate effects, and the way I described it was it takes some energy to create a fold. We still have the fold right here. And the fold could happen slowly by itself, but you have to give them some time. It's everything jumps around, and it's not, you don't know when that's going to happen. If you try to go really fast, then a lot of times you'll need more force. So the plasticity, the yield criteria will be higher for a higher deformation rate, generally. Anisotropy means that how much energy it takes to shear on one side of those boxes we talked about is different than the other box. And there are ways to deal with it by modifying. Look, here we decide to go take the whole plasticity solution based on a value of C1, but a material constant. But people put material constant to these individual differences, square differences, to account for anisotropy, essentially. So that can be done. For processing, you can control the hardening. And I mentioned a couple of times about temperature. You can put alloys, small amounts of alloys that will also affect the dislocation multiplication and how it heals back after the fact. You can put precipitates. So it's something that we engineer for a specific application. We also try to work in compression. The aluminum cans that we're all familiar with, they don't get drawn up in the air, normally in dies, to generate strong compression conditions, so you can keep yielding without breaking them. And at the end, for cars, for aluminum cans, there's a strong orientation effect that's created in the material in those grains. And we've circulated examples of grains that you can see as you deform, they show up. So the grains are very important, and their orientation and their crystal texture will also affect how you can deform them. And that will be part of our processing lecture. Any question, anything that some aspects I try to go a little faster, a little slower. Yes?
So if you do tension on all sides, volumetric expansion, it doesn't yield ever. You were saying you need to have a difference in stresses on all three sides.
Yeah, if it's just a pressure, then you're just changing the distance between the bonds.
So if you have a compression, it crushes eventually. Well, what happens when you have tension all the time? It will never yield.
Yeah, you'll reach fracture, and there are other criteria where instead of having a cylinder, it has hands on it. So if you reach a certain amount of triaxial tension, you start breaking.
The stress tension, the 9 components. The hydrostatic component is sigma 1 plus sigma 2 plus sigma 3, and that's equal to the hydrostatic component. When that has no effect on shear or fracture. The other 6 components, this is actually what I was going to talk about briefly. First of all, there's actually only 3 of them that are independent. Okay, the other 3 that he didn't write down are equal to sigma 1, 2, sigma 1, 3, and sigma 2, 3. Those 3 are the shear components. The other 3 are the tensile components. And if you have your, can you go back to your Mises
yeah.
cylinder that goes up in 3 dimensions?
I think
Okay.
I think this is kind of what.
Go back to the graph.
Yep.
That one right there. The hydrostatic component will not cause deformation, and that's why we use hot isostatic pressing. Isostatic compression will not deform, change the shape of something. You can put a chess piece in a high isostatic press, and it will come out shaped like a chess piece when it's all done.
Unless you reduce porosity, right? Unless you reduce porosity.
Right. If it has porosity, I was actually going to talk about that on Monday. You're jumping ahead. So a submarine is not going to fail at the bottom of the ocean from any shear. There's no shear on it. It's all hydrostatic if it's a solid. Okay? It's actually hollow, so there actually is some shear on it. But if it was a solid lump of something at the bottom of the ocean, it's not going to deform. And that's what I'm going to be. He's talking about. He's going to be talking to you about damage tolerance and fracture, but I'm going to be talking about metal forming, and so this stuff is critical. And in fact, if you go back through the first chapter of Hosford's book, which I gave you, Simone's been going through that first chapter and giving you the basics. If he hadn't done this lecture, I would have had to do it, so thanks. Okay?
It's 1 through 3 we did, really.
And what I'm going to talk about on Monday is how everything you've learned before has been uniaxial tension. You learned about tensile tests? Well, what in deformation is uniaxial tension? Nothing that I know of. Everything is biaxial or triaxial, okay? And so, for my part of the course, you're going to have to learn about biaxial and triaxial, and they'll put up the von Mises ellipse. The von Mises ellipse is just a plane skewed through this hydrostatic cylinder. You got your von Mises ellipse, there you go. That ellipse is just a piece of that cylinder. The hydrostatic, that sigma 1 plus sigma 2 plus sigma 3 has nothing to do with deformation processing, except that it can suppress fracture. And people do things like hydrostatic extrusion, and they can extrude brittle materials that otherwise would fracture if you tried to just push them out of a toothpaste tube, right? So this stuff is, you know, it's back in the math, and I hate math. But actually, I don't hate math. I just think it's sort of a waste of time to tell MIT students about it. Anyway, so let's just, did you have some other things you needed to do? I just
Well, I mean, the wrap-up is keep in mind the stress-strain curve. The reason I derived it, we talked about it, is it doesn't have anything to do with really the fracture. It's just a tool. Definitely it gives you the initial yield, right? So you can put that into the von Mises, gives you some idea, it gives you the hardening exponent, which you can also use. But that's about what we get out of a stress-strain curve that's very scientific in detail. After that, the fracture depends on your specimen geometry, and we talked about that. For strain hardening, I think it's important you keep in mind that it's rate dependent. I hope we talked about that enough when we went through the dislocations at the beginning and the battlefields. And hope you had a good day.